Give me 1 second, George.
No problem.
Okay, so I think we're going to go ahead and dive into lutetium-hafnium. George is going to walk us through the theory, and this is super cool and gets complicated quickly. So take it away, George.
Okay, so we're kind of done for day one talking about chronology, and now we're going to start talking a little bit about some of the other complementary things that we can measure that help us say a little bit more about what was going on with the rock besides just the age. So remember in my first introductory part, I was saying that, you know, geochronology is cool because we can use these minerals to not just say something about time, but we can say something about other processes that were taking place when those crystals were forming. So just to give you some examples, maybe these are ones you know of. You can look at titanium and zircon. You can look at zirconium and titanite, and they'll tell you something about the temperature at which the mineral was crystallizing. You can use Raman to look at inclusions in zircon grains and other minerals. They tell you something about the pressure that that mineral was crystallizing at. You can look at oxygen and lithium isotopes in zircon and other minerals, and that would say something about the fluids that were present, the origin of the fluids that were present in that magma when the mineral was forming. You can look at magnetite inclusions and say whether there was a magnetic field on Earth at the time when that crystal was forming, very important for early Earth minerals. You can look at carbon isotopes and say something about biogenic processes. So these are all the other cool things that you can measure in these geochronologic minerals, and they'll tell you something about the other processes that were going on. People think about geochron minerals as kind of time capsules, and I think that's true. They're great for telling time, but I think of them more as maybe sort of crystal messengers. They come from deep in the earth, they come from back in time, and they carry with them information about all sorts of different processes. And it's our job to try to figure out how to read that information from these different crystals. So the next two modules are ones that Sarah and I will be working through that kind of talk about two of the complementary things you can measure in geochronologic minerals that will tell you something else about the processes that were going on when those minerals formed. And the first one I'm going to jump into is lutetium-hafnium isotopes. And it's all about radioactive decay. It's the same kind of things that we were talking about in geochronology. We use the same instruments, laser ablation, ICP-MS. But I want you to not really think about time so much, more about processes that are taking place within the Earth that we might be able to reconstruct by looking at these isotope ratios. So here's our playing field on this diagram. And what you can see is that there are 6 different flavors of hafnium, isotopes 174 to 180. 5 of them are stable, not radiogenic, but 176 is the decay product of lutetium-176. So you can see that with the arrow. There are 2 flavors of lutetium, 175, 176. 175 is stable, 176 decays to hafnium-176. And then you go down to ytterbium, it goes from 168 to 176. And those are all stable. They're not decaying over time, so they stay the same over time. But ytterbium 176 is important for this because your mass spectrometer cannot tell the difference between any of these masses at 176. The mass spectrometer can't distinguish hafnium 176 from lutetium 176 from ytterbium 176. And unfortunately, all 3 of these elements are present in most of the minerals that we're going to use for this isotope system. So this is going to be a little bit more complicated than when we are using the mass spectrometer to do uranium and lead isotopes. We talked about that interference of mercury with lead. That was kind of a complication, but here we have this really big interference between hafnium, lutetium, and ytterbium. So bear that in mind. This is going to be a little bit more complicated. Let's kind of go to the next slide and take a dive down deep into the earth and kind of see where this process is taking place. Sarah, if you can advance us. Sorry, you'll have to do these for me. We're going to dive down into the mantle. So on the upper right diagram, the dark brown on the right, that's the mantle. Crust is up in the upper part there. You have advance me again, please. And let's start off in the peridotite. Now we're going to go back up one. I'm not sure why it advanced. There we go. Let's think about the peridotite. We're down in the mantle. There's some lutetium, there's some hafnium, there's some ytterbium down there. And remember that the lutetium is decaying to hafnium over time, hafnium-176, whereas the hafnium-177, 178, 180, those are staying the same. So think about that peridotite, the 176, 177 ratio of hafnium in the peridotite is going to increase in time, right? Because lutetium-176 is decaying to that peridotite. Okay, let's do something interesting. Let's partially melt that peridotite and take some of that magma and bring it up into the crust like you see on the right in a subduction zone. And that magma is going to crystallize into a granitoid, some kind of a nice looking granite. And in this one, it's a little bit different. The lutetium tends to stay in the mantle, whereas the hafnium goes up into the granitoid. It's incompatible. And so the hafnium increases relative to lutetium. So still a little bit of lutetium, but there's a lot of hafnium. And so now over time, the 176, 177 ratio is not going to change all that much, right? Because there's not as much lutetium decaying to hafnium. So peridotite, that ratio is going to change a lot. The granite, it's not going to change very much. But now let's go to that zircon crystal, which is forming in that granitoid. When the magma crystallizes, maybe 0.1% will crystallize into zircon. Zircon has a huge amount of hafnium. Look at that, 15,000 ppm, a few percent. And it has very, very low lutetium. And so think about that 176, 177 ratio in that zircon. It's not going to change very much at all, right? Because there's very little lutetium there, but lots of hafnium. And so that's why this is, the lutetium-hafnium system is not really a great chronometer. We don't use this for dating processes because it would be like a zircon that has no uranium, but a tremendous amount of lead, right? There's no parent, no lutetium, and a lot of hafnium, the daughter. And so this is not a great chronometer. Let's see if we can draw this on a diagram that kind of shows how these three different reservoirs are going to change through time. Let's say that we have some peridotite, we make a granite, and we crystallize a zircon right at time zero, 4.5 billion years ago. The green line is now going to go up to the left, and that's with a y-axis that shows 176. Can you see that? 176 hafnium to 177 hafnium. That 176 to 177 ratio is going to increase in time in the green line in the mantle because there's lots of lutetium, right? So that's going to increase in ratio. Whereas continental crust, maybe the granite, you can see the red line down there, the solid red line, it's going to increase, but it's not going to increase as fast as the mantle. And that's because there's not as much lutetium in that granite compared to the mantle. And then check out that zircon, the red dashed line, that hardly changes at all. And that's because there's very little lutetium in the zircon, but there's lots and lots of hafnium. So that tiny little bit of lutetium decays, but there's so much hafnium that 176, 177 ratio hardly changes at all, even over a long period of Earth time, 4.5 billion years. So this kind of shows the three main reservoirs of interest on Earth: the mantle, continental crust, and zircon. Geochemists like to when they talk about how the mantle and the crust are behaving, what they like to do is they like to put those two reservoirs together into what they call the average Earth, or the bulk silicate Earth, or the chondritic uniform reservoir. And so that's the blue line on here. The blue line is kind of the average of the crust and the mantle. And the reason that geochemists like to do that is because we know exactly what that blue line has done through time. That's because we have meteorites. Chondritic meteorites tell us what that average Earth evolution has been like through time. So we actually know that blue line very well. And what we're interested in is how the green line and the red lines change on Earth. And what they also do is they tend to use units like Epsilon units. You probably have heard of that before, or delta units, sort of smaller divisions. And so what we're going to do is we're going to take that average Earth blue line and we're going to call that our reference. And we're going to assign that to an epsilon value of 0. And then we're going to talk about changes of the mantle and changes of the crust relative to that blue line to Chur. Okay, so fasten your chin strap. Here we go. Where we started was the upper right. Everything is increasing in ratio over time. And now we're going to say average Earth, the blue line, we're just going to call that 0. It's not changing in epsilon value, whereas the mantle is becoming more positive and continental crust and zircon are becoming more negative. In reality, they're becoming positive in ratio but because we assign Ch to the value of 0, they become more negative relative to Ch. So is everybody confused now? So we do this just to make these numbers easier to memorize. When you go to GSA and you're going to talk about your sample, you don't want to be talking about a ratio of 0.28213 versus 28217. Nobody's going to know those numbers. But if you say, oh, my sample's +7 and yours is -3, well, people are going to know something about those numbers. And so these epsilon units just make it much easier to talk about positive mantle-like evolution versus negative crustal-like evolution through time. So that's why we use these epsilon units. Everybody good? This is just the diagram that we're going to use for this hafnium isotope system. We'll go to the next one. Okay, so let's just see how this might work. Let's start off time 0, 4.5 billion years ago. The mantle, that gray line, is trucking off to the upper left. Looks like it's going to end up around +16, something like that for the mantle. That's the mantle array. But now, instead of making a granitoid 4.5 billion years ago, let's crystallize a granite and crystallize a zircon 3.7 billion years ago. We'll do this by partial melting of that peridotite. And so we're going to take off from that gray line. We're going to move down to the left along the red line. That's going to be the evolution of the zircon line. In ratio, it's not changing very much because there's so little lutetium, but relative to the Ch line, it's becoming more negative, right? So it's sloping downward. So that's what it looks like if you melt a granite, melt the mantle, make a granite 3.7 billion years ago. Next one. Let's do the same thing. Now let's have a melting event, and we'll say that maybe 750 million years ago, we had some kind of a continental collision or subduction magnetism. We started to melt some of that peridotite in the mantle, and we made a granite 750 million years ago. That red line then shows how that zircon is going to evolve through time from that magma 750 million years ago. So to do this, we need to measure the hafnium isotopes to do the epsilon value, but we also need to know the uranium-lead age, and that's why these two systems work so closely together. You have to do uranium-lead to get the age, and then hafnium isotopes to know whether you're mantle-like or crust-like. Okay, so that's pretty simple. Go to the next one. So you might think, well, wait a minute, this does kind of look like a clock. If we measure our zircon and we're down at -50, well, the way you're going to get there is by we follow the blue lines back up. Oh, it must have been Archean melting to make that granite. You measure a value that's -30. Oh, that must be Proterozoic. You measure a value that's 0 or -5. Oh, that looks like that's Neoproterozoic or Paleozoic. And so in this very simple system, the value that you measure for epsilon hafnium, it does have some time significance. The more negative it is, the older the material must be that created that very negative epsilon hafnium value. Okay, so this is a very simple system. As you probably know from your igneous petrology classes, this doesn't happen very often. It doesn't happen very often that you can take a peridotite and partially melt that material and make a granite. So you know what happens more commonly in the next slide. We'll go to the next one. This is a rare process, the next slide. This is a little bit more common. So what usually happens is you melt the peridotite, it goes up into the lower crust. You see that blob in the lower part of the crust. That might be where we have this migmatite or mash, that grayish diagram in the middle. We think that's what the lower crust looks like. It's kind of a hot, mushy, mashy, semi-molten zone with lots of different components, over billions of years, lots of magma has moved up through the crust. So there's probably lots of different ages of material that are all mixed up there. And that's kind of intermediate composition. And then you can melt that material and make a granitoid. And so when people talk about generating granite melts, felsic melts, it's usually a two-step process. You don't get granite right from the mantle. Instead, you get it from the lower crust, partial melting of lower crustal migmatite and mash. And so now let's imagine the granitoid. It's got the zircon in the lower right. And what we're going to do, we're going to come along today and we're going to measure the hafnium isotopes in that zircon crystal. It's going to say something about the granitoid. It's going to tell us a little bit about the migmatite and mash, but it really doesn't tell us much about the peridotite because it's a two-stage, at least two-stage process. So we'll go to the next diagram. So the green line is what you can't do. What you can't do is look at the zircon hafnium isotopes and say something about what was taking place in the peridotite. All that zircon tells you about is what's going on in the granitoid and the parent rock, the source material for that granitoid, that migmatite. But that migmatite is hugely complicated. There could be lots of different peridotite melting events to create that migmatite. So the zircon doesn't tell you anything about mantle extraction. So now let's see if we can do this same thing on the hafnium evolution diagram. Let's go to the next slide. So now let's go on the left. This is what we measure. You had a good day in the lab. You measure a -28 epsilon unit for your zircon. You go to the E2 and you measure the uranium lead age. You get an age of 750 million. So what you do is you take the red star. This is time 0. You correct back now using that lutetium-hafnium ratio, even though it's very small. You correct that back along the red dashed line. But you can only go back as far as 700 million, right? Because that's the age of your zircon crystal. The zircon's 700 million. It doesn't tell you anything that was about what was going on during the Archean. It's only 700 million. Can't have any information about Archean processes. But you want to know something about the origin of that material that was melted 700 million years ago to make that granitoid. So the different color arrows there show you some of the different possibilities. If it's single one-stage melting, like we said at the beginning, it would be that red line. And then you would say, oh, red line, it hits the DM line at what, 2.3 billion years ago. Looks like we had melting of the mantle 2.3 billion years ago. But the problem is that mash, that migmatite, it actually could consist of the blue arrows. There could be some material that came out in the Archean, the lower blue line, but it's a 50-50 mix. There could also be some younger blue material. Maybe it came out of the mantle 1.7 billion years ago. So your red star, it could actually be a 50-50 mix of the two blue arrows. And now you have a very different history of mantle melting, right? Instead of one stage at 2.3, now you've got two events, 2.7 and 1.7. Or let's go crazy. Let's look at the extreme, the green arrows. Now we've got some Hadean melting 4 billion years ago. And we've also got some melting, the small green arrow just a couple 100 million years ago. And you combine those two together, 50-50, and you could end up on that red star. So very different history for that migmatite mash. So this is what I mean, that what you measure today, it tells you something about what was going on back to the age of crystallization, but then it doesn't really tell you anything about what was happening before the age of crystallization. Could have been one phase of melting, could have been 2, could have been 20, and you have no way of reconstructing that. And so that's why we can't really use these hafnium isotopes as a clock, because you don't really know what was going on in that system prior to the formation of that granitoid. Oops, can we go back to the slide? Very good. Let's go to the next one. We do have some general terms that we can use. We can talk about if you have a -40 or 50, everybody would say, oh yeah, that's pretty evolved. It's been around a long time. Down around -10, -20, people would say, oh, that's kind of an intermediate value. If you're up in the positive area, people would say that's juvenile. And juvenile, you know, that means it's kind of primitive, but it also means it's pretty young. And so we use that term juvenile to say you're up in the positive world. It was material that came out of the mantle pretty recently, whereas those high negative values are pretty evolved. They tell you it's kind of an old system. So there's a little bit of time information, but only in a very general sense. Okay, let's go to the next one. Okay, so now I'm going to diverge a little bit and talk about how you measure the hafnium 176 and 177 in zircon. And this is where it gets kind of detailed and kind of technical. But I think it might be interesting for you. You are going to spend some time with mass spectrometers, and what you're going to see is a lot of different analyses of different standards, maybe some solution analyses, and you're going to be talking about epsilon units, and you're trying to get down to 1 epsilon unit. What does it take to get 1 epsilon unit of a hafnium determination? And so we're going to grind through this. It's a little technical, and then the good thing is when we come out of this, Sarah is going to take us through some data sets, and we'll be able to use what we've learned about hafnium to say something about cool processes that have taken place in the Earth back in the past. That's kind of the fun part. So let's grind through this. Let's go to the next slide. And here, kind of like we did for uranium and lead, these are all the different isotopes of interest, 171 to 180. Those are all the different isotopes that we're interested in. And remember, we've got 3 different flavors here. We've got a terbium, lutetium, hafnium, and there's 6 isotopes of hafnium, 2 isotopes of lutetium, and 6 isotopes of the terbium. But keep your eyes on the prize. We're interested in the middle ones there, 176, 177. And the complexity is that 176 actually consists of a little bit of a terbium in blue, a little bit of lutetium in green, and a lot of hafnium in red. And the bad news is that your mass spectrometer can't tell the difference between blue, green, and red. All it can do is measure 176. So if you come along today and you measure 176, 177 of your zircon, it's not going to be hafnium 176, 177. It's a mixture of hafnium plus a terbium plus lutetium 176 divided by 177. So we have to do 5 corrections to get down to red 176, hafnium 176, and compare that to hafnium 177. And this is a super complicated system that we use of doing these corrections. This was figured out by some really smart people. You can see them on the left there. These are kind of the founding fathers of hafnium isotopes. And these are the folks who figured this out. And you have to do this with great precision. Remember when Kurt and Sarah were talking about uranium, lead, and Wei also, they were talking about, we're hoping to do maybe 1% uncertainty on these uranium lead ages. That's a good day. For this, you want 100 times better than that. You want 0.01% precision. So upper right, this is kind of like having a target. You're out doing archery. It's a target on the end of a football field. And the bullseye, your target is a 1 centimeter little red spot, and you're trying to see that at the other end of the football field. So this is a pretty precise aiming system that we have here. And we have to do these corrections really, really precisely. So that's the target on the right. If you do this in terms of numbers, you might measure a value like 0.41272 is what you measure. And you're going to apply these corrections, and you're going to end up with a number like 28224. And that number has to be precise to 0.00003. That's what 0.01% precision is. So you got to do the corrections really carefully. Hafnium is a super tedious method in the laboratory. I'm going to walk you through these 5 corrections just to kind of show you the ingenious nature that these geochemists figured out how to do this. And you'll be doing this when you come to the lab. So we start off with the bad news that the hafnium isotopes in your zircon, the ones you measure with your mass spectrometer, are not the true ratios. I'm not sure we've made this point before, but your mass spectrometer never actually measures the correct ratio of any isotope system. You're always off by a little bit. You always have to calibrate it or correct it by some amount. So for hafnium isotopes, we call this the beta, or the mass bias correction, and it's big. It's about 1.5% per mass unit. So 176, 177, that's a correction of 1.5%. That's pretty big when you're trying to get 0.01% data. So we take advantage of the fact that there's lots of different hafnium isotopes. We measure 177, 179, that upper bracket. We know what that ratio is in nature. We measure it with our mass spectrometer. We never get the right answer, but we use that as the correction. That's a 1.5% correction. And then we'll use that to correct our 176, 177, which also is a little bit biased by the mass spectrometer, that same bias factor. So we take advantage of the fact that there's lots of different red flavors of hafnium to do this fractionation correction for hafnium isotopes. That's number 1. Next one. Number 2, well, bad news. It turns out your mass spectrometer doesn't give you the right ratio for terbium isotopes either. But the good news is that we know the 177, 173 ratio, the upper bracket on the left. We measure it. Oh, you're off by 1.5%. Well, cool. We'll just use that as the correction factor. And that's what we're going to use to correct the 173 to 176 ratio. So that little blue 176, we're going to be able to correct that for fractionation, because we know what the 171, 173 fractionation is. Good. Correction number 2. Next one. Well, that little green bar of lutetium there in 176, turns out that also has a little bit of mass bias, a little bit of beta correction is required. The bad news is that there's only 2 isotopes of lutetium. There aren't a whole bunch of stable isotopes of lutetium like for hafnium and ytterbium. But it turns out that lutetium behaves pretty much the same as ytterbium in the mass spectrometer. And so we can use the ytterbium mass bias, the 171, 173. We'll use that correction factor and we'll apply that to the green ones. It's not perfect, but it turns out to be a pretty good, pretty reasonable correction. So that's number 3. So we've corrected all 3 of our isotope systems now for this mass bias. And the next one. So now we're going to try to figure out how to subtract out that blue 176, that little blue box of 176. It turns out we know what the 173, 176 ratio is in nature for ytterbium. So we just measure 173, calculate how much 176 is there. We've already done the beta correction. So we just subtract out the 176 based on how much 173 is in the system. And that turns out to be a big correction. This is the biggest correction of those 5. If you don't do this one right, you'll end up with a hafnium epsilon value that's way off. And we'll do number 5 here. This is a simple one. We're going to do the same thing with the lutetium. Turns out we know what the 175, 176 ratio is in nature of lutetium. So we measure how much 175 is in there. That tells us how much 176 is in there of lutetium, and we subtract that out. And guess what? Now we just have the red 176 and the red 177, and that's what we want. We want hafnium 176 to hafnium 177. And so that's the isotope ratio that we're going to plot on this evolution diagram. But to get there, you have to do all these other measurements. You have to measure all these other isotopes of ytterbium, lutetium, and hafnium. And you have to measure those other isotopes to about 0.01% to be able to do all those corrections very reliably. We'll go to the next slide. Okay, so that's kind of that was the hard part. I hope you were able to follow those corrections. And you'll see how when you come to the lab or other labs, other people's labs, you'll see how these corrections are done. They'll be able to walk you through those different corrections, and you'll be able to look at the magnitude, the impact of each one on that final uncertainty. To do these measurements, we're going to do it exactly the same way that we do uranium lead. You can actually do it at the same time. You can ablate into a zircon with the laser pit going down. You can have some of the signal going to one mass spec, do uranium lead, some of the signal going to the multi-collector and do the hafnium isotopes. We call that split stream. You can do that and get uranium lead and hafnium at exactly the same time. And the next one. And to be able to prove that your data are correct, of course, we analyze lots of standards. Just like for uranium lead, I think Kurt was showing you that we do one standard and then 5 unknowns and one standard and 5 unknowns. Well, here for hafnium, to make sure you're doing this really well, really precisely, you're actually going to do about twice as many standards as you do unknowns. The good news is that we pay for all those standard analyses. You don't have to pay for those. You pay for the unknowns. We pay for all the standards, and we're just trying to ensure that your data are really, really good. One of the things that we do is we put a solution into the mass spectrometer. So not a zircon, we have a solution that we know the hafnium isotope concentration in. We make a cocktail out of this hafnium solution. We put different amounts of lutetium and ytterbium in there. We know what the ratio of that solution should be, 28216. This is another one of those magic numbers. If you're having a good day, then you're talking about 28216. If you're having a bad day, oh, it's 28223 or 28214. Life is not good if you're in that world. So you're hoping for 28216. And the next slide. And then here's what the mount looks like for your zircon analyses. All of your unknowns are in the upper half. All the lower ones down there are the standards. And you can see we use usually about 7 different standards. And these are all the standard zircons that have been analyzed for hafnium by other people, FC1, Plizovici, 91500. We know what those values are. We're going to measure them in your session, and hopefully we get the same values, the true values, the known values, and then you'll feel confident that your unknowns have reliable hafnium isotope data. And we're going to plot those up on the next diagram. And so here's what that looks like. The horizontal lines are the known values for our different standards: Sri Lanka, FC, 91500, Mud Tank, Tamora. And then the vertical bars are our measurements. And hopefully The red measurements lie pretty close to the red dashed line, the true value. The gray measured values lie pretty close to the dashed line, the true value. So this is what we do. And this is what you want to see when you come to a lab and do hafnium isotopes. You're going to probably spend half a day or maybe a whole day analyzing standards first. You're going to generate this kind of data. When you're sure that your standards are sitting right on top of those known values, then you get the green light and you're good to go with your unknowns. And chances are, it's 10 o'clock at night, so you're going to be there through the night measuring your unknowns. If not, then you come back the next morning, you're probably going to have to start over with those standards because the machine will have drifted during the night. So when you come for a hafnium session, bring some friends. It's going to be 24/7, and you'll probably get the best data if you can keep running through the night. So next one. So here's what it looks like. We'll do this kind of quickly, just like Kurt showed you the beam trace for uranium lead. Here's what the beam trace looks like for hafnium. We do not go fast for this. Going fast is not the game for hafnium. You want the best precision you can get. So you see we keep the laser on for about 60 seconds. We use a pretty big spot. We drill down pretty deep into the crystal, and that's just to get that really high precision, that 0.01% precision. Next one. And so let's begin to look at some data here. And this is going to kind of feed us into what Sarah is going to do. We're going to start off on the left. We're at time 0, right? We're doing this today at 0. So we're going to make our measurement of hafnium isotopes. The measured value that you're going to get is not like 0.282 something. It's like 0.4, 0.3. So you're like 4 stories up. You're doing these corrections down, 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 and you hopefully do those corrections well. So you end up down at 2812 or 28213, something like that. Then you're going to correct that measured value. You're going to go back in time to the age of crystallization. So you have to know the uranium lead age for this to do it. You're going to use the measured lutetium-176, hafnium-177 ratio. If you're lucky, it corrects all the way back to the gray line, that depleted mantle line. And then it tells you, oh, look, 3 billion years ago, that zircon was formed by melting of the mantle. Hey, this is a one-step process. 3 billion years ago, we had this melting event. We made some juvenile zircon right by melting that mantle peridotite. So we would call that a juvenile zircon coming right out of the mantle. Okay, but that doesn't happen very often, right? You don't usually make granite right from the mantle. So let's go to a more realistic example, the next one. It's going to be more like this. You're going to do your corrections. You'll end up with your measured value at time 0. You're going to correct back to the uranium lead age. In this case, it's what, about 2 billion years ago. That's the age of crystallization. And that's as far as you can go. You can't go farther than that because there is no information in that zircon about what was going on before 2 billion years ago. It's a 2 billion-year-old crystal. It doesn't tell you anything about what was going on during the Archean. Sorry, my dog's helping me here. So what you can do is go back to the black line, but you don't know if it was moving back along the black question mark back to Archean, the green question mark, Proterozoic. You don't know about that earlier evolution. We'll go to the next one. Okay, so let's do our first data set that we're going to look at. These are now some detrital zircons. This might be like from Western North America. We call these the 3 fingers of North America. 1.7s, 1.4s, 1.2s, the main basement provinces, maybe a little bit of Archean in there. You don't really need to do hafnium isotopes on all of these analyses. You don't want to do 600 hafnium analyses. Instead, what you're going to do is you're going to pick just a few grains from each of these age clusters because it takes so long to do the hafnium measurements. You don't need to do all of them. Pick a few representatives and do the hafnium isotopes on those grains. So let's do that next.
That's my job, George. I think we're at the end of your slide deck.
Okay, so that's what Sarah's going to do next. She's going to take this data and she's going to talk about the history in the southwestern part of North America based on the analyses of those the 3 fingers from North America. But maybe we'll stop there and see if you have any questions about the method. Let's make sure everybody kind of understands the theory, how you do the measurements, how you do that data reduction, make those 5 corrections. When we're all good with that, then we're going to do the fun part. Sarah gets to do the fun part, talking about what these data mean. So questions? Okay, Sarah, are you ready to press on?
You guys feel okay with this? Yeah, sort of, maybe.
I'm going to stop recording and start a new one for your session.